Welcome to Turing Point YouTube channel, on combinatorial optimization from a new perspective. We have so far addressed different results on pedigree polytopes. In this episode, episode 8, we define and study the multicommodity flow problem to prove the necessary and sufficient condition for membership in pedigree polytopes. Videos on pedigree polytopes. Presented by Tiru Arthanari. Proudly sponsored by Whole New World Limited, New Zealand. Once we have ensured that Fk is feasible and we have identified the rigid arcs in Fk, and find Rk, the set of rigid pedigrees and their weights given by mu. Then, after updating the node and arc capacities in the network, we obtain the new layered network, Nk, Rk, mu. If Nk is empty, we can conclude X given k plus 1 is in convex Pk plus 1. Why? This is because we have a set of rigid pedigrees, Rk, with weights given by mu. Notice that the total weight of mu equals 1, since the node capacities of nodes in stage k-2 add up to 1. Thus, X given k plus 1 is a convex combination of the rigid pedigrees with the given weights. However, to check this network is well defined, we need to solve MCF K. We explain the objective and constraints of this problem first. The commodities in the network are defined first. Consider the network Nk, Rk, mu. For every arc in the set of arcs in Nk accepting arcs in N4, designate a unique commodity S. Let S denote the set of all commodities. We write a double arrow S and read A designates S. Let SL denote the set of all commodities designated by arcs in FL. Next, we define what we mean by a pedigree agreeing with an arc in FL. The arc is connecting an origin in FL to a destination in FL. Either X, R, given L, is a rigid pedigree ending in node U, or X, R, given L, has E, L, an edge chosen at the L-3rd stage. And at the L-2nd stage edge, E, L plus 1 is chosen. That is the pedigree path for X, R, shares arc, A, prime in F, L. Different pedigree paths are shown in different colors. The pedigrees, X, R, are shown in the figure, with matching colors. Some of these pedigrees agree with an arc, A, prime, and they contribute to the flow along arc, A, prime, like the black, orange, and blue pedigrees. Pedigrees that agree with an arc A, designating commodity S, contribute to the corresponding commodity flow, like the orange pedigree contributing to commodity flow 4, S. Orange pedigree agrees with arc A, prime, so contributes to the flow of S, along arc A, prime. The multicommodity flow problem. Some notation. Let C suffix A denote the capacity of arc A in the set of arcs for the network Nk. Similarly, let Fa denote the flow along arc A. We define F super S suffix R as the flow of commodity S along arc A. We have the following restrictions in the problem. At each intermediate node, V, we have flow conservation for each commodity as given in equation 3. Next, we require the total flow of all commodities in S suffix L through an arc to be equal to the arc flow F A See equation 4. Let V suffix S be the total flow of commodity S through an arc A. So for each commodity S in S suffix L, we have FA is equal to V suffix S for the arc A designating S. See equation 5. At each node V in NL, we have node capacity restrictions satisfied, that is, total flow of all commodities in S suffix L along arcs entering node V is less than or equal to the updated node capacity X bar V. See equation 6. For all origins in stage 1, and for all rigid pedigree nodes in the network, namely R, Q, for Q in 4 to L-1, we require availability restrictions to be satisfied. See equations 7 and 8, respectively. We have, in addition, the node capacity restrictions as shown in equation 9, for nodes in stage L-2. The objective in the problem MCFK is to maximize the total flow along arcs in F, K, equivalently, the sum of commodity flows, Vs, for S in S, suffix K. Thus, we have explained the multi-commodity flow problem, MCF, K, as stated in the book as problem 5.1. We make some easy to observe facts on the problem. Firstly, the maximum possible flow Z star in this problem is at most 1 minus the sum of mu p, for p in the set of rigid pedigrees, R, K. We call that possible maximum Z max. If Z star equals Z max, then the bundle capacity X bar V at each node V is saturated. We shall show in the next 2 episodes the important result that a necessary and sufficient condition for X to be in convex Pn, the pedigree polytope for N, is that the optimal solution Z star to the problem MCF N-1 is equal to Z max, the maximum possible value.